Okay, good afternoon. Thanks all for coming out. So I'm going to be telling you about SiFive's AI solutions, what we've been doing that's new. We have a big announcement, but we've been working in this area for a while. So I want to start out with talking about AI and what that means to us as an IP company. So we're providing AI solutions, and when we talk about providing a solution, what does that solution have to do? So AI, the important thing to note about AI, it's not an application. It's not a little box you have on the side that does one thing. AI is going to be infused through all the other applications in the system. It has to work with all the software. It's really a capability, a technology. It's not an application, right? And for a solution, that means we have to make sure we can support a wide range of devices. You already saw how wide our product portfolio is, everything from microcontrollers to data centers. We really want a solution that spans that space. And because we're spanning such a big space, we have to address all these different performance latency requirements. Also, even in a given space, I'm optimizing for latency or throughput or memory capacity. What am I optimizing for? What kind of algorithms am I running? Right? So our solution has to adapt to market-specific constraints. Memory capacity, bandwidth, technology that's available, size of the system. So we really need to provide a flexible hardware and software solution that can scale across all these dimensions and also integrate the AI into the general application. We're not just building a stunt box that runs something off to the side. It has to be integrated with the main application and scale across all these sizes. And the reason we want to scale it, we want to maximize the investment in AI software. So a common software platform that can run across all these scales. So that's the nature of what a good AI solution looks like. Now the challenges with AI, the first and most obvious one to most people, it requires an intense amount of compute. Just a tremendous number of operations need to be performed. A lot of memory has to be trolled through to run the big models. So a tremendous amount of compute is needed. This motivates a lot of folks to go build some custom stunt boxes that are really good at doing some kinds of compute. However, the other big challenge in AI, it's changing fast. So you have this tremendous rate of evolution in the AI models, the structure of the models, the data types they use, the kinds of memory capacity and bandwidth they need. So there's this constant evolution, which really makes it hard to build a single stunt box that's going to work well into the future. If you over-optimize, you're not going to work for tomorrow's AI algorithms. And so a lot of these challenges really are because AI is really in this relatively early stage. We're still developing it out. It's still a new thing. So there's a lot of innovation, a lot of development. So again, we need something flexible, but it has to have very high compute, and it has to be programmable. And we need to integrate it with applications. That's another problem with having a little stunt box on the side. It's not like a video codec, for example, where the standards are all very well understood, and the interface to applications is very well understood. Your AI model may be doing predictive text, it may be doing object recognition, it may be large language model serving, very different use case. So it really has to be meshed with all different kinds of software. Now, RISC-V in AI. Now what's interesting, sort of Patrick alluded to this early on, when we started RISC-V, it was actually in the context of building application-specific processors. And so our design goal, and this was before this wave of AI, back in 2010, before AlexNet and the whole deep learning thing took off, we wanted to build something that was very efficient and stable, but allowed extensibility. And so with RISC-V now, we come up with this open standard ISA anybody can use. That means we can build a rich general software ecosystem around this open standard. But the way we designed RISC-V was made it easy to add your own extensions on the side without messing up the standard software ecosystem. A lot of people get this confused and think, oh, there's going to be all this fragmentation in RISC-V. We carefully designed it so the standard software keeps running on the standard part of your architecture, but you can innovate off on the custom side. And so this combination of a standard set that supports standard software plus a playground where you can try new things is why it's a great match for AI. So when we designed RISC-V, we did actually think of vectors at the very beginning, because in the previous generation of AI back in the 90s, I worked on vector machines for AI. And so I knew vectors were going to be important. So when we designed RISC-V, we made sure we'd have a very good vector extension. So there is a standard RISC-V vector extension that's ratified that actually has a lot of support for the things you need in general AI. So for example, it was designed to support mixed precision operations very efficiently, much better than the competing architectures in doing that. But at the same time, as well as having this standard high-performance vector extension, we have space to add more specialized AI extensions where we can add new features and really optimize for this. Now, as a result, a lot of people also saw this. RISC-V has now become effectively a standard architecture in the AI space. So we just list some of the adopters of RISC-V. Google, Meta, NVIDIA are all using RISC-V in their AI solutions, right? And in fact, most of the new startups in this space, many of them are using RISC-V as the basis of their experiments in this place. So RISC-V, this mix of standard rich software ecosystem plus the flexibility of innovating, that's really attracted folks into using RISC-V for AI. So that's RISC-V and AI. So I want to talk now about SiFive products in AI. So the SiFive intelligence line we introduced a few years ago. So today I'll tell you about the next step in our products. But just to go back and remind you, our goal with the first couple of generations, we had previous 2 generations of these X cores, was really to enable our customers to bring in their own AI acceleration into a common platform. And so we had the 2 previous generations, the X280 with the X288, and then the second generation X380, X390, which we introduced about a year ago. One of the things we learned working with our customers in this space, they needed a way to attach their own AI engine into a general system. So we worked with them to define a very efficient interface that allowed them to bring their accelerator into a standard software environment running RISC-V. And this was really and also these X cores have very efficient standard vector compute, plus some extra extensions to help with AI. And these have been very effective. So just to recap what we did. So the first generation was a 512-bit vector length. X280 was the initial product. X288, I'll talk about this, is the enhanced version for NASA, the space computer mission based on space computer based on the X280. Last year we introduced the X390, X380, and this, the 390 in particular, was a 4x improvement in overall compute throughput over the X280. We basically made it twice as wide in vector length, but also doubled the number of functional units. So we went from 1 vector ALU to 2 vector ALUs. We went from a single load store pipe to a separate load pipe and store pipe. So the 4x came from twice the width and twice the number of functional units getting to the 390. So that now has 1K-bit vectors and also a wider coprocessor interface. Okay, so that was the previous product. These have been very successful. We had a lot of design wins with these products with various customers. Some of them we can name, some of them we can't. So very high-profile customers are using this to build their AI solutions in everything from automotive applications to really edge computing out in space to high-end data center applications as well. So these products are already out there, already being used by customers, taking our intelligence cores, adding their own accelerators, and building systems. So I just want to highlight the space one a little bit, just to give you some idea of how pervasive AI really is. So NASA really wanted to take AI capabilities out into space for future missions because they wanted more autonomy in their future rovers and satellites and probes. And they saw a need to really up by about 1,000x the amount of compute they had versus their previous solution. And so it was a very intense competition. We won this competition, and we basically took that X280 core we had and added a lot of features to do with resilience, reliability, fault tolerance around those X280s to make an 8-core system that's going to be the standard NASA mission computer going forward. Now, one thing I'll point out, as John alluded to a bit earlier on, we have an extensive automotive product portfolio. A lot of these features for reliability, resilience, these are the kind of features that will trickle down into the automotive products as well. So you can view this as a precursor to sort of future intelligent automotive products with higher reliability and resilience. Now, a lot of the other customers for these products, the way they're using them is really, as I mentioned, attaching their own accelerator IP to our X cores. So now what our X cores are providing is RISC-V standards, wide vectors, RISC-V standard vectors, a high-performance memory interface that scales and is scalable and coherent, and a supported software stack. And this is very important for the vectors. We support RISC-V standard vectors, as SiFive We spend a lot of energy on vectorizing compilers, vector intrinsics, high performance libraries for those vectors. And all that goodness is what the customers are really appreciating, because often their accelerator only handles a few small kernels, right? And most of the complexity of a real AI application is in the other code, not just the accelerator piece. But we allow them to take that accelerator and attach it through a very high bandwidth interface to our X cores. And so to give you an idea, this on each core in the X390, you have nearly a terabyte a second of bandwidth between the accelerator and the vector registers inside the X core. So very high bandwidth connection to the accelerator. But what the customers are really getting is a very quick way of getting from their accelerator to a complete system that runs standard RISC-V software. So that's very powerful. This is what customers really appreciate about our intelligence cores. Now, software, I keep mentioning software. So SiFive, we've been investing heavily in AI software stacks. And here we've been leveraging the open source ecosystem out there, particularly around IRI, the IRI stack. So I've been working with partners on some components. Some components, the green components here, are the ones that we've primarily been driving. The blue components, we've been working with collaborators out in the open source community to bring this up. So this is a stack that can take models, TensorFlow, Onyx, PyTorch, bring them in and compile them down to our intelligence cores, going through these frameworks. So some of the key components and what we've been developing are the LLVM compiler that targets our backends, our cores, our particular microarchitectures, the system software and runtimes that run across our cores, the SiFive kernel library, which are handwritten routines that provide highly optimized versions of libraries that drive the vector unit on our cores. And we all integrate this into the standard framework to make it easy for customers to get their models running on our intelligence cores. We also provide the facility so our customers can insert the custom instructions that drive their custom accelerators and integrate that into the same software stack. And so this helps our customers get a good start by having this reference software stack they can just take and use to get going on building their AI solution. Just diving down one level into the compiler, this is based on MLIR. So it takes in the graphs at the top, does a whole bunch of stages of compiler optimization that ends up mapping down to code that's then scheduled at runtime onto intelligence processors. And support a lot of the common frameworks, targets our CPUs. As I said, it allows the customer to add in support for their accelerator into this tool chain. And so we're working on supporting a lot of the key frameworks. And as I said, we've been working this for over 3 years, and we continue to work on this with our customers and partners. The kernel library. So the compilers are great and everything, but to really get the most performance, you really need hand-coded routines at the bottom. So every framework relies on somebody sitting and hand-coding the key kernels. We have a great team at SiFive who've been working on this, not just for AI space, but other high-performance numeric libraries, such as signal processing. And we have a library we call SKL, or SKIL, the SiFive kernel library. And some news today is we're actually going to be open sourcing this library to help drive innovation in the space, and so enable our customers and our customers' customers to quickly get good performance out of SiFive cores and microarchitectures. All right, so let's talk about, that's our existing product stack. That's been out for a few years. I want to talk about the next step, which is the XM series. That's what we're announcing today. So the XM is giving customers a new choice. So previously we had the X series cores with an interface so the customer could add their IP in. With the XM, a lot of our customers said, well, and actually it's funny talking to all these customers and all their secret source, they all had their own secret source, but it was actually all the same thing almost. So we're now providing a standard matrix engine that plugs in to the back of our X cores. I'll go through the details of this. So now we're giving the customers a choice. They can either add their own engine or take the AI engine that we're providing in the XM series. And again, we're supporting this in the SiFive's AI software stack to target this thing directly right now. And this will complement our existing portfolio. As I said, we're not removing this option. We'll keep this option as well. Customers are invested in their own accelerator, but now providing a new facility with our own matrix engine. So what is the XM? So when we took a look at AI workloads, one thing we saw was there's this balance of scalar, vector, and matrix compute, and it varies depending on the kind of model you want to run. The size of the matrix you operate on how much vector compute you need. And so we wanted to build a balanced cluster that could handle everything reasonably effectively. And so the cluster contains 4 of our X cores with wide vectors based on the X390. So these have 1 kilobit vector registers in each of the cores, standard RISC-V standard vector registers. They all connect to a single large shared matrix engine. So the matrix engine does matrix multiplies. It does basically fat outer products. So it's like an outer product, but slightly deeper to get greater efficiency. So you're doing a m by n times in a dimension of k matrix multiply on this matrix engine. Each of the cores thinks it has its own unique matrix engine attached, a separate state for each core, but it's physically shared set of functional units. This allows any one of the cores to do matrix multiplies, and actually a single core can keep the whole matrix engine busy, but if you have more complex workload, any of the cores can be doing matrix multiplies interleave with other cores loading and unloading matrix contents from the matrix array. And in some applications, what you'll find is one core is driving the matrix engine, the other 3 cores are running vector code to handle the activation functions around the side of that matrix operation. So these 4 cores are connected to a shared level 2 cache, and there's a coherent memory system. I'll talk about scaling in a minute. But in addition, each of the cores also has a dedicated high bandwidth path to memory coming out of each core. We call the core local port. Now this allows the customer to build very high bandwidth customized memory system. One example could be this all connects to a large shared scratch pad that's on cache memory off to the side, and you have high bandwidth out of each core. Some customers will attach memory mapped accelerators or local scratch pads off of each core. So we give customers a lot of flexibility in these 2 ways of connecting to the core, either the coherent memory system, which is cached, or through the non-cached direct access through the high bandwidth memory interface, these core local ports. Okay, so we define these 2 high bandwidth ports. So the total bandwidth in and out of this cluster is up to 2 terabytes a second of sustained bandwidth. It's basically 1 terabyte a second on the high bandwidth core local ports and up to 1 terabyte a second on the shared memory port to talk to this core. So the X cores are based on the X390. We've also enhanced those. We've added some new features. One example is we've added new instructions to accelerate exponential calculations. So now a single core can do up to 64 exponentials per cycle per core in those accelerated units. This is to speed up things like softmax operations on the vector units. So we've enhanced the cores as well for AI. The matrix instructions, they just sit in the regular RISC-V instruction stream on one of the cores. When you issue a matrix instruction, it takes vector operands from the vector registers, sends them to the matrix unit, does an outer product, which is accumulated in the state inside the matrix engine. So you can quickly and efficiently do large matrix multiplies over there. We'll be supporting a range of different data types. The initial versions of the product, these are the primary data types we're supporting. For the source data, int8, BF16, FP16, FP32, and FP64. For the accumulators, the initial product will support 32-bit integer and float 32 accumulators, as well as FP64 accumulation. Later versions, we are planning additional data types driven by customer demands and models. For example, we will later eventually be supporting the MX data types down the road, but this is for the initial product. And also we'll be supporting, depending on the model, we can configure these to, as Patrick mentioned, we use generators to build our cores, and so we can optimize away the data types not needed to build different products for different product segments, but with the same overall architecture driving it. So the matrix engine, the largest designs, to give you an idea of the throughput, a single cluster can support up to 16 TOPS per gigahertz of int8 multiply add, and up to 8 teraflops of BF16 per gigahertz. As I mentioned already, with a sustained bandwidth of up to 2 terabytes a second in and out of each core. 1 terabyte a second through the shared port, and 1 terabyte a second through the local ports on the cores. So now scaling this design up, we designed this cluster. So depending on demands, it could be the only thing you have in a small system, but you can also scale this up now to build much higher throughput systems. So using the shared interface talks Chai, just as we're doing with the data center product 870D. So now we can scale up to many of these clusters connected on the coherent memory port through Chai, but also the customer can then build a very high bandwidth uncached memory system using the high bandwidth core local port interface as well. So if you want to build large scratch pads or HBM coming in directly and not going through the shared memory interface, you can do that. So the shared memory is typically used to help the cores synchronize and the runtime to manage work queues. And the high bandwidth core local ports are typically used for accessing the big data sets that you're crunching on in these applications. Now, in a lot of systems, this will be used as a device and will be attached to a host CPU. So host CPU can be RISC-V. Some of our customers are using an ARM host here to connect to these clusters, or an x86 even driving this. So again, we're an IP provider. We provide a flexible range of solutions. We have many customers in different spaces. So our goal is to build something flexible that can be used many different ways. Now the scalability, some of our customers are building very large systems, and you can tile these clusters up to get very high levels of performance. So based on our initial studies with some of our lead customers in advanced technology nodes, we expect to actually see better peak numbers than, for example, NVIDIA Blackwell in comparable technology nodes with this technology. It obviously depends a lot on the customer technology they're mapping to and the size they decide to build. But in terms of raw compute density and efficiency, we think this will enable our customers to get higher performance than the industry leader in those nodes. And why can we do that? Well, we're really targeting this area. It's not a GPU. It's designed to be a compute engine. And so we believe that's why we're getting this greater efficiency in this space. So just going to finish here. So we view RISC-V as really is really the starting point of AI. AI is just starting. It looks like it's been going for a while, but it's just the beginning of AI. It's really going to be next multiple decades of AI going on. There seems to be this real consensus around RISC-V and AI, like I mentioned, having an open platform that's flexible, can run a standard stack, but can be extended without disturbing the standard stack. That's the power of RISC-V. We already have the X series. The base of this is already in flagship customer silicon. We have multiple wins in silicon of the base core. And by adding this XM series, taking a look at what customers wanted, we put this together to give customers a coherent package now where they can go build these scalable AI solutions across the big wide space. Okay, so thanks. That's the AI part of the presentation. Just to summarize, so at SiFive, we want to be the leaders in RISC-V, driving the standards, driving the most advanced technology implementations, and getting out to the best silicon. That's really what we're trying to do at SiFive. Okay, thanks.